6 అయిందా? వెయిట్ చేయి. Good evening, students. So welcome to GTQ course. So we Made Easy faculty want to support the student community before the GATE examination. In Made Easy we have completed the regular course. In regular course we have solved various numericals, concept oriented, and after completing the regular course we have supported the students by giving quick revision program, and apart from quick revision program we have also given RTQ course that is related with revision through GATE questions. In RTQ course also we have solved in power electronics very advanced level questions. So before going to the examination part, first we have to summarize the basic concepts of each and every chapter. For that summary is already given in Made Easy, and after summary solve all the workbook numericals at least 2 to 3 times. And in power electronics 3 chapters, rectifiers, inverters, choppers are very important, and you can go through that. If you want additional advanced level questions in power electronics, you can refer CTQ courses and RTQ courses. CTQ and RTQ courses are for advanced level questions in power electronics. And apart from that, just before the GATE examination we are going to support the student community by giving some important questions for GATE 2022. Okay, so now let us solve some of the questions. So here only 1 hour is allotted for power electronics in GTQ. So in this 1 hour I am going to solve as many questions as possible. Let us go through the first question now. I hope it is audible, students. Just tell me whether it is audible or not. Dear students, is it audible? So very good evening, Mr. Yadav and Dixit. Okay, very good evening, Swami Gupta, Sagar Gupta. Very good evening all. So just I'll give the questions, take only 1 or 2 minutes, solve the questions. Be fast, and accuracy is very important here, right? Now go through the first question. So the average output voltage of a full wave rectifier is, so here it is a diode bridge rectifier. Across that resistive load on DC side we have connected a filter capacitance. AC supply is 120 volts at 60 hertz. Load resistance is 500 ohms, and capacitance, filter capacitance is 100 microfarads. So we have to find out the average output voltage in this case. Okay students, I'll give you 1 minute to solve this question. Consider that you are attempting the GATE now. Okay, so just I will give you 1 minute, make it fast. Okay, solve this question. A full wave diode bridge rectifier, load is pure resistive load on DC side, we have connected filter capacitance. So here we have to find out the average output voltage after connecting filter capacitance. Okay, yes, make it fast. Only 1 minute I am giving. Dear students, without filter capacitance I think we have already discussed in the regular course. Okay, with filter capacitance. Very good evening all. Thank you for your compliments. Yes. I'll give you a hint for this. First draw the output voltage waveform in this case. I hope everything is visible and clear to you. What is the output voltage waveform? What is the output voltage waveform? Here, without filter capacitance, what is the waveform we get? So just see here, without filter capacitance, if I am not having filter capacitance here, so you will get a waveform like this. So this is the waveform you will get without filter capacitance. I hope you are familiar with this waveform. So this is without filter capacitance. So here we get maximum average voltage is 2 Vm by pi. So without filter capacitance we get average voltage. So without filter capacitance. So after using filter capacitance, I hope this is the waveform after reaching steady state. I am directly drawing the steady state waveform. So directly we are drawing the steady state waveform. You can see the waveform now. So this is the steady state waveform. So this angle theta, this angle is beta. So the diodes are conducting between the limits theta and beta. So this is the steady state output voltage waveform after conducting filter capacitance. During the interval theta to beta, when the diodes are conducting, load is connected to the supply. So this is same as supply voltage. At beta, when diode stops conducting, this capacitor discharges to I square R losses. So current decays exponentially here. So this is the output voltage waveform in this case. Okay. So now here, if you observe here, the peak voltage of the supply. So this is the peak voltage here. This is Vm is the peak voltage. So what is the ripple in the output voltage here? Can you tell me what is the ripple in the output voltage here? Just see here. You can see the ripple in the output voltage. So this is delta Vr. So delta Vr is the ripple in the output voltage. I will give the expression for ripple in the output voltage with filter capacitance for resistive load. You have to remember this expression. So here the ripple in the output voltage delta Vr. So I am giving the expression for the ripple in the output voltage delta Vr. So that is equal to Vm by 2 into F into RC. Okay, F is the frequency of AC supply, Vm is the peak voltage of supply, load resistance and filter capacitance. So ripple in the output voltage is inversely proportional to the capacitance value. As the capacitance value increases, see here, as the capacitance value increases, we can minimize the ripple voltage. Okay, in rectifiers frequency is constant, it is 60 Hertz. So supply frequency is constant. So by using high values of filter capacitance, we can minimize the ripple in the output voltage. But in this case, we are asked to find average output voltage, right? So we are asked to find average output voltage. So how to find average output voltage in this case? See, whenever there is ripple in the waveform, we can find out the average voltage like this. Average voltage. See, suppose if capacitance is infinitely large, the ripple voltage is almost zero. If the ripple voltage is almost zero, then average voltage is almost equal to peak voltage. So when average voltage is equal to peak voltage, if the filter capacitance is very, very large, ripple voltage is very small when you compare with the peak value. If the ripple voltage is negligible when you compare with the peak value, then average voltage is almost equal to Vm volts. But now, due to the ripple, the average voltage is reduced by delta Vr by 2. So you can see here, the average voltage passes almost to the center of the ripple here. See here, I will draw the average voltage waveform here. Let me draw the average voltage waveform here. It will pass through the center of the ripple here. So I am drawing average voltage. I hope it is visible to you. This is the average voltage. It is exactly passing through the center of the ripple. So how to find average voltage here? This voltage is Vm. This voltage is Vm. And this voltage is approximately half of delta Vr. So this is approximately half of delta Vr. I hope you are understanding. So this voltage is Vm. So what is the average voltage expression? Average voltage is equal to Vm minus half of delta Vr. So Vm minus half of delta Vr or delta Vr by 2. So this is the expression for average voltage. Of course, it is an approximate only. Error is negligible here. No need to worry about this error. So this is the expression. So now average voltage equals to Vm minus, what is the expression for ripple in the output voltage? The ripple in the output voltage is Vm by 2f Rc. So here 2 is there. So it is Vm by 4 into f into Rc. Okay. So dear students, you have to remember this formula, average voltage. This is the expression for average voltage. I think you can calculate this value. So that is equal to Vm into 1 minus 1 by 4 times f into Rc. Okay. So that is equal to, the peak voltage of AC supply is 120 into square root of 2. Okay. 120 into square root of 2, that is the peak voltage of AC supply, minus 1 divided by 4 into frequency is 60 hertz. Frequency is 60 hertz. Load resistance is 500 ohms. Load resistance is 500 ohms. And then capacitance value is 100 microfarad. 100 microfarad. Okay. So just simplify this value. Just simplify this. Tell me what is the answer, students. Calculate this value. Tell me what is the answer. Yes, make it fast. Dear students, calculate the value. Calculate the value. Some of the students have given correct answers. I appreciate them. Yes, make it fast. Tell me what is the value. So its value is 155.54 volts. Yes, Mr. Saurabh and Mr. Pradham, very good. So 155.54, 155.54 volts. Okay. So here, dear students, you have to remember the formula for ripple in the output voltage. Once again, I am repeating this. So in the case of full wave diode bridge rectifier feeding resistive load with filter capacitance, this is the expression for ripple in the output voltage. Okay. Ripple in the output voltage depends on the capacitance value. If I use very large filter capacitance, okay, then ripple is almost 0. When ripple is almost 0, average voltage is almost equal to peak voltage of AC supply. Okay. Now, due to this ripple, average voltage is slightly decreased. So here average voltage passes through the center of the ripple almost. So this is ripple delta VR. So I want to find average voltage. Average voltage is equal to Vm minus half of delta VR. Vm minus half of delta VR. So using this expression, we can get the expression for average voltage. Okay students, I hope you understood this point. Yes. So very good students, Mr. Gaurav, Ajay. So everyone has solved the questions. Really appreciate you. Okay. Yes. Now let us go through the next question. Here in this case, suppose same question, they are asking PIV of Thyristor. Dear students, can you answer my question? Can you tell me what is the PIV of Thyristor in this question? Yes. What is the peak inverse voltage rating of a diode? Yes guys, solve this one. What is the PIV rating of diode? What is the PIV rating of diode? Same question. I want to find out the PIV rating of diode. Anyone? PIV rating of diode. Yes, make it fast. Yes, find out the PIV rating of diode, dear students. Yes, respond to me. Be fast. It's very easy question. Find the PIV rating of diode. You can see here, when in the positive cycle here, when these two diodes are conducting, this positive voltage appears here, minus will appear here. So the entire source voltage appears across this. So that means the maximum negative voltage that appears across the diode is equal to the peak voltage of AC supply. So what is the peak voltage of AC supply? That is 120 into square root of 2. Okay students. So 120 into square root of 2. So that is the PIV of the diode. Right students. Now Now same question, small modifications I will do it. See, I will do small modification now. Can you try to find PIV of this in this case? So small modifications, dear students. So see this question. Just go through this question. So that means diode bridge rectifier PIV depends on the circuit. Okay. So just see this one. Yes, dear students, can you tell me? So here the supply voltage is 120 volts 50 hertz. Okay, supply voltage is 120 volts 50 hertz. Now can you tell me PIV rating of diode? What is the PIV rating of diode in this case? Yes, dear students, try to answer this question. What is the PIV rating of the diode in this case? Can you tell me what is the circuit diagram? If you carefully observe here, this circuit diagram is a voltage doubler circuit, right? So this is actually in a voltage doubler circuit, right? It is actually a voltage doubler. So if the filter capacitance is very large, then output voltage is almost equal to double the peak voltage of AC supply. Suppose if the filter capacitance is very large, the output voltage is almost double the peak voltage of AC supply. It is a voltage doubler circuit. See, okay. Now in this case, what is the PIV of the diode? Yes, can you answer this question? See the difference between this question and the previous question. In the previous case, PIV of the diode is Vm. See, in this case, PIV of the diode is peak voltage of AC supply. Okay. Whereas in this case, what is the PIV of the diode? So just observe here. The upper capacitor is charged with Vm volts. Okay. See here. The upper capacitor is charged with Vm volts. Even bottom capacitor is charged with Vm volts. We are assuming that filter capacitance is very large. Because when you design the ratings of diodes, we have to be prepared for the worst case. So for the worst case, let us assume very large filter capacitance. So output voltage is the voltage across each filter capacitance is almost constant at Vm volts. I hope you understood. Now in the positive cycle, which diode is conducting here? Just observe here. Which diode is conducting in the positive cycle? So this diode will conduct in the positive cycle. So that means this diode is charging the upper capacitance. See here. This diode is charging the upper capacitance like this. Okay. So now what is the voltage that appears across this diode? So tell me, what voltage appears here? So this diode is charging this upper capacitance. This diode is charging the upper capacitance. Okay. Now what is the voltage across this one? The voltage across the bottom diode is 2 Vm. Can you tell me the reason? See, when the upper diode is conducting, this terminal is connected here. So the voltage, this diode is in the off state here. This diode is in the off state here. Okay, upper diode is conducting. That means this is short circuit here. So that means what is the voltage across the bottom diode? This is Vm plus Vm, 2 Vm. So PIV of the diode is 2 Vm. So here PIV of the diode is 2 into Vm in this case. So 2 into 120 into square root of 2. So that is the PIV of the diode. So here PIV of the diode is 2 Vm. Even average voltage is 2 Vm because it is a voltage doubler circuit. I hope the concept is clear. So any doubts, dear students? Just observe here. See the difference between the two circuits here. So in the first case, PIV of the each diode is Vm volts. Okay, here filter capacitance is directly connected across the resistive load. Here in this case, the maximum output voltage. What is the maximum possible output voltage here? The maximum possible output voltage is Vm here. Okay, so in this case, See, in this converter, what is the maximum possible output voltage? The maximum possible output voltage is Vm if filter capacitance is very, very large. If filter capacitance is very, very large, the maximum possible output voltage is Vm. Whereas in the second case, it is a voltage doubler circuit. Okay, the average output voltage is double the peak voltage of AC supply. I hope you understood, students. Right. So concept is very clear. Dear students, I have mixed questions here. Okay. So 1 or 2 questions are tough. Most of the questions are moderate questions, or 1 or 2 questions are easy questions. So combination of all questions are given. Okay, students. Yes. So I hope everything is clear to you. Yes. Very good. Good response from you. Thank you, students. Go through the second question, dear students. Yes. Now see the second question. All of you go through the second question now. So just go through the second question. I hope everything is visible to you, right? Okay. So it is a DC to DC converter which is shown in the figure. The duty ratio is 4/5. Okay. We have to find out the peak forward blocking voltage across the switch. 4 options are given. Option A 4000 volts, option B 4200 volts, option C 1000 volts, option D 200 volts. So we have to find out the blocking voltage of switch. Yes, dear students, did you identify the circuit diagram here? So did you identify what is the circuit diagram here? First identify the circuit diagram and then try to find out the peak voltage of the switch. Yes, make it fast. I'll give you 1 minute time. Speed with accuracy is very important. First identify what is the converter here. It is mentioned DC to DC. Is it buck converter or boost converter or buck boost? Yes, make it fast. Yes, what is your answer? Yes, students, try to answer the question. First identify this one. Yes, it is actually a buck boost converter, right? But we are having a transformer here. So it is an isolated buck boost converter here, right? So this is an isolated buck boost converter. It is an isolated buck boost converter. Right, students? Given duty ratio alpha or capital D, it is 4/5. We have to find out the blocking voltage of the switch. Yes, students, in the second mode you see, just go through the second mode. In the second mode, switch is in the off state and then diode starts conducting. Actually what happens in the first mode? In the first mode, when the switch is on, diode is in the off state. Okay, in the second mode, when you disconnect the switch, diode starts conducting, right? What happens when diode starts conducting? When diode starts conducting, the secondary voltage, this is V0 here. This voltage is V0. Okay, when this voltage is V0, so what is the primary voltage? Can you tell me? The primary voltage is, see, turns ratio of the transformer is 1:5, right? So what is the primary voltage? Primary voltage is V0/5. See, secondary voltage, when diode is in the on state, secondary voltage is V0. Both the voltages are same. So when secondary voltage is V0, primary voltage is V0/5. Okay. So now what is the voltage? Here switch is in the blocking state, no? So now what is the voltage across the switch here? The voltage across the switch is, see, minus plus. So here if you observe here, can you tell me what is the voltage that appears across the switch here? What is the voltage that appears across the switch here? Yes, tell me. What is the voltage that appears across the switch? See, this voltage is negative as per the reference here. Am I right? This voltage is negative as per the reference here. So just observe here. So already when diode is conducting here, see, this is the direction of current here, right? So this is plus and this is minus here. As per the reference it is negative. I will give the reference voltages plus minus V1 plus minus V2. Okay. So when diode is conducting, V2 is equal to minus V0. Just observe here, secondary voltage is minus V0. Okay. I am giving for same dots plus sign. V2 is equal to minus V0. So what is V1? V1 is equal to minus V0 by A. Minus V0 by A. Minus indicate that actual voltage is negative as per the reference. Now what is the voltage across the switch here? Now the voltage across the switch is, supply voltage is Vs. So therefore the blocking voltage of switch, the blocking voltage of switch is equal to Vs plus V0 by A. I think this formula already given in the regular course. This is actually a flyback converter, isolated buck boost converter. Blocking voltage of switch is Vs plus V0 by A, where A is the turns ratio. A is equal to N2 by N1. So A value is 5. Now we have to find out the average output voltage. What is the average output voltage in this case? So just observe here. What is the expression for average output voltage here? Average voltage, isolated buck boost, A times alpha Vs by 1 minus alpha. So V0 is equal to, A value is 5, alpha is 4 by 5 into supply voltage is how much? Given supply voltage is 200 volts divided by 1 minus 4 by 5. Okay students, so calculate this value. You will get average voltage is 4000 volts. Okay, average voltage is 4000 volts. So blocking voltage of the switch is, supply voltage is 200 volts plus 4000 volts divided by turns ratio is 5. So calculate this value. Just calculate this value and tell me what is the answer. You will get 1000 volts, right? 1000 volts. So that is the blocking voltage of switch. So answer is option C here. Option C is the right answer. So I hope everyone understood. So this is a little bit easy question here. So option C is the right answer. The blocking voltage of each switch, the blocking voltage of the switch is 1000 volts here. So I hope everyone understood this question. So Punit Sharma, are you okay with this? Now actually I have drawn the reference polarities. Actual polarities are opposite to the reference polarities here. If you observe here, this is actually the reference polarities. See, when you turn off the switch here, the actual polarities will reverse here. See, when you disconnect the switch, until the switch is on, the transformer is storing the energy. It is magnetizing. When you disconnect the switch, voltage will reverse both the sides. Secondary side voltage will reverse, primary side voltage will reverse. So voltage will reverse, actual voltage will reverse both the sides. So now if you observe here, this value is V0 by A. Okay. So what is the voltage across the switch? Minus plus minus plus. So Vs plus V0 by A. So voltage across the switch is Vs plus V0 by A. So that is the formula to find out the blocking voltage of each switch. Okay students, I hope you understood. Right, very good. So go through the next question now. Next question. So question number 3. Just observe here. Question number 3. Question number 3. A thyristor is having I square into dt rating 20 ampere square seconds. So, you know, I square T rating. Why I square T rating is specified for thyristor? Dear students, can you answer this question to me? I square T rating. Why it is specified for thyristor? So, I square T rating of thyristor. Can you tell me why this is specified? See, we have to select a fuse or circuit breaker for overcurrent protection of thyristor. Okay. So, I square 2 rating is specified for thyristor to select a proper fuse for its overcurrent protection. I hope you understood. So, in this case, it is a very simple circuit here. Here, it is used in the supply. It is used to supply the circuit shown in the figure. When a fault occurs, it shorts the 15 ohm resistor. So, I think it is visible to you or not? See. So, just go through the circuit diagram. Whenever there is a fault, it shorts the 15 ohm resistor. So, that means, so it will short this 15 ohm resistor here. See here. This will short this 15 ohm resistor to ground. So, when 15 ohm resistor is shorted, what is the equivalent circuit? So, we have to determine the shortest fault clearance time to be achieved if no damage occurs to the thyristor. That means we have to find out the fault clearance time. So, how much time the circuit breaker can take to clear the fault such that SCR does not damage? You understood the question? How much time the circuit breaker or fuse can disconnect the circuit? What is the clearance time such that SCR does not damage? So, that is called fault clearance time. So, we have to find out the fault clearance time such that SCR will not damage. So, that is the given question. See, here it is shorted. 15 ohm resistor is shorted to the earth. So, when 15 ohms resistor is shorted to the earth, we have to find out the shortest fault clearance time. Okay. Yes, try to answer this question. Once again, I will read out the question. A thyristor has I square into dt rating is 20 ampere square seconds. So, given I square into dt rating, I square into dt rating, that is equal to 20 ampere square second. So, that is the I square into dt rating of thyristor. Now, the short circuit occurs across the 15 ohm resistor. See, the short circuit due to some fault, the short circuit occurs across the 15 ohm resistor. That means 15 ohm resistor is shorted to earth. Now, we have to find the shortest fault clearance time. The shortest fault clearance time to be achieved if no damage occurs to the thyristor. I hope you understand. Now, when the 15 ohm resistor is shorted, what is the equivalent circuit? When the 15 ohm resistor is shorted, I will draw the equivalent circuit. Here 1 ohm, 1 ohm. So, this is anyhow, see, this is anyhow shorted to the earth. This is anyhow shorted to the earth. Okay. So, this is 120 volts and 60 hertz. So, this is shorted to the earth. Okay. This is shorted to the earth. Can you tell me what is the fault current for the worst case? See, when do you get maximum fault current? We get the maximum fault current when the short circuit occurs exactly at the peak voltage of AC supply. That means exactly at 90 degrees. When the fault occurs at 90 degrees, the supply voltage is peak value. What is the peak value of AC supply? 120 into root 2. So, for the worst situation, if the fault occurs at 90 degrees, see, we have to be prepared for the worst case, right? So, for the worst situation, so you can see here, for worst condition, for worst situation, for worst situation, for worst situation, let the fault occurs, let the fault occurs at omega t is equal to 90 degrees. So at 90 degrees, the supply voltage is peak value. So what is the peak fault current here? So therefore, the peak fault current. Therefore, the peak fault current in the given circuit is equal to the peak voltage of AC supply by 1 ohm resistance. See here, the peak fault current is equal to the peak voltage of AC supply by 1 ohm resistance in the circuit. This is 1 ohm resistance, 1 ohm. So peak voltage of AC supply is 120 into square root of 2 by 1. This is the peak value of fault current. Because we are discussing for the worst situation, we get the peak value of fault current if the fault occurs at 90 degrees. See, let us assume that for the worst case, when the fault occurs at omega t is equal to 90 degrees, the supply voltage is peak value. It is 120 into root 2. So the peak fault current in the network is 120 into square root of 2 amperes. And it is very clearly given that integral of the fault current whole square into dt, okay, is equal to how much it is given? 20 ampere square. 20 ampere square into seconds. Integral of 0 to clearance time. So TC means clearance time, fault clearance time. Here TC is called fault clearance time. So how to find out the fault clearance time? The peak fault current is 120 root 2. See here, the peak fault current is 120 root 2. So integral of 0 to TC, the peak fault current is 120 into root 2 whole square into dt is equal to 20. Okay, so what is the clearance time? So from this you can say the clearance time. Calculate the clearance time here is equal to 20 divided by 120 square into 2. Yes, just calculate this value, dear students. Tell me what is the answer here. What is the answer here? 20 divided by 120 square into 2. If you calculate, you will get 0.69 milliseconds. 0.69 milliseconds. Okay. So dear students, I hope you might have done this. Okay. 0.69. Okay. Yes, Aditya. Very good. Aditya has done this. 0.69 milliseconds. So yes, Vivek Roy, you are done. So 0.69 milliseconds, option B is the right answer here. So that is the fault clearance time. Okay. So whenever there is a fault occurs across the 15 ohm resistance, 50 ohm resistance is shorted to the earth. So that is the equivalent circuit. The maximum fault occurs at 90 degrees. At 90 degrees, the maximum fault current is 120 into root 2, the peak voltage by 1 ohm. You will get the maximum fault current. So after calculating the maximum fault current, you can find out the clearance time. The fault clearance time is 0.69 milliseconds. Okay, students? I hope you understood. Right. Go through the question number 4. Yes, go through the question number 4. Yes, all of you go through the question number 4. So I hope it is visible to you, right? Once again, I'll read out the question. You can see the circuit diagram here. The switch is turned on in each half cycle at alpha is equal to 30 degrees. The switch is turned on in each half cycle at alpha is equal to 30 degrees. The power factor at the input supply is, so find out the power factor at the input supply. Yes, try to solve this one. First of all, what is this circuit diagram? Can you tell me what is this circuit diagram? Yes. What is this circuit diagram? Is it rectifier or AC to DC or DC to DC or AC to AC? Can you tell me what is the circuit diagram here? Yes. Answer to my question. What type of configuration it is? 4 diodes and 1 switch is there. So between these two terminals, it is a 4 quadrant switch. Okay, this is a 4 quadrant switch. You see here, we are having diode, 2 diodes. Okay, and then switch. So take it as anode and cathode. Okay, this is actually a 4 quadrant switch. This is equivalent to 2 anti-parallel thyristors. This is equivalent to 2 anti-parallel thyristors, anode and cathode. Or this is equivalent to a track. This is equivalent to track. It is actually a 4 quadrant switch. So this is what students should understand. This is actually a 4 quadrant switch. Okay? Okay, students, I hope you understood. So it is actually a 4 quadrant switch. It is actually a 4 quadrant switch. So it will support all the 4 modes equivalent to a track. That means it is AC to AC conversion. So supply is AC side, output is also AC side. So that is actually a 4 quadrant switch. We are having different types of 4 quadrant switch, different configurations. In regular course already we have discussed. So this is actually AC to AC converters, right? First of all, what is the waveform in this case? In this 4 quadrant switch, what is the waveform you will get here? So just observe here. So this is our supply voltage. This is our supply voltage. So let us draw the output voltage. So it is triggered at alpha is equal to 30 degrees now. So you can see here it is triggered at alpha is equal to 30 degrees. So here this is 90, 45 and 30. So this is alpha. This is pi plus alpha. So alpha is equal to pi by 6 radians. That is equal to 30 degrees. So we are triggering the switch at alpha. So let us draw the output voltage waveform here. So see the circuit diagram. So first go through the circuit diagram properly so that you can draw the waveform now. Okay. Yes. See at alpha in the positive cycle I am giving gate signal for the switch. So when the switch is turned on, see the which diodes will conduct here? When the switch is turned on, D1 will conduct here. After that switch will conduct. Okay. And like this, then D2 will conduct. So the circuit is closed like this. I hope you understood. So which diodes are conducting? D1, see the current direction. D1 switch and then D2 and then load. So D1 switch and D2. So that load is directly connected to the supply now. So alpha to up to pi radians, D1 switch and D2 will conduct. Okay. So D1 switch and D2 will conduct. So when D1 switch and D2 will conduct, V0 is equal to Vs. So V0 is same as the supply voltage. Okay. So alpha to pi, V0 is same as supply voltage. Because it is resistive load, D1 the current becomes 0. When voltage becomes 0, current becomes 0 because it is resistive load. After that all the devices are in the off state. So output voltage is 0 here. Then again in the negative cycle what happens? When the supply polarities reverses. So just observe the negative cycle. In the negative cycle when the supply polarities reverses, Now which diodes will conduct here? D3 and D4 will conduct in the negative cycle. Of course the switch also will conduct. So in the negative cycle the current direction will reverse. This is the current direction, like this. Switch will conduct and then D4 will conduct. So this, that means V0 is equal to Vs only now also. So which diodes will conduct here? D3, D3, switch, and then D4 will conduct. D3, switch, and D4 will conduct. Okay. Now V0 is same as Vs here. So this is actually AC voltage controller. So AC voltage controller, right? So that is the expression for output voltage. Okay. So this is the area of the waveform. So this is actually AC voltage controller. For resistive load, voltage waveform, current waveform are similar. For resistive load, what is the expression for calculating the power factor here? How do you calculate the power factor? So just equate input power is equal to output power here. Just equate input power is equal to output power. Power balance equation. Input power, supply RMS voltage, supply RMS current into power factor. What is output power in the case of resistive load? V0 RMS, V0 RMS, I0 RMS. Okay. So now here in this case, supply RMS current and output RMS current are same. So they will cancel. So therefore power factor is equal to, output RMS voltage by supply RMS voltage. This formula is applicable only for pure resistive load. This formula is applicable only for pure resistive load. Dear students, I have discussed this in regular course also. One pulse converter in rectifiers, single phase, half wave rectifier or full wave rectifier, whenever the load is pure resistive load, this is the expression to find power factor. The same expression is also applicable even in AC voltage controllers with pure resistive load. Okay, RMS output voltage by supply RMS voltage. Now how to find RMS value of output voltage in this case? So now we have to find out the RMS value of output voltage. Yes students, can you find out the RMS value of output voltage here? See, whenever you have symmetrical negative pulse, if I square the positive pulse, same you will get if you square the negative pulse. So whenever we have symmetrical negative pulse, then directly you can find RMS value for half cycle, you get the same result. So out of half cycle, so 1 by pi integral alpha to pi, equation of the output voltage is Vm sin omega t, square it. So Vm square sin square omega t, Vm square sin square omega t into d omega t. So just whole power 1 by 2. So if you simplify this expression, you will be getting Vm by square root of 2 into time period of each pulse is pi, pi minus alpha, upper limit minus lower limit, plus half of sine 2 into alpha minus sine 2 pi is 0, whole power 1 by 2. So that is the expression for RMS value of output voltage. Then how do you calculate supply RMS voltage here? See, the equation for supply voltage is Vm sin omega t, right? This is the equation for supply voltage. So what is supply RMS voltage? So it is Vm by square root of 2. So now let us find out the expression for power factor. So power factor is equal to V0 RMS by supply RMS. So if you divide by Vm by root 2, Vm by root 2 will cancel. This is the expression for power factor, 1 by square root of pi into pi minus alpha plus half of sine 2 into alpha whole power 1 by 2. Okay. So just simplify this value. Given alpha is equal to pi by 6. So here substitute alpha is equal to pi by 6 and then calculate the power factor. Okay students, all of you calculate the value. Tell me what is the value finally. Make it fast. What is the value? Yes, most of the students have already calculated. Yes, Swati Gupta, your answer is correct. Okay. So answer is 0.985. 0.985. So that is the power factor here. Okay, right answer. Okay, students. Okay, go through the next question. Okay, question number 5. All of you solve this question. Yes, please note down the question. So it's a DC to DC converter. You can see here a DC to DC converter. Can you identify what is the converter here, dear students? Identify what is the converter here. So just identify the converter here. Is it buck converter or boost converter or buck boost converter? See, sometimes they will not mention what is the converter. We have to identify what is the converter. Inductor is connected to the supply side. So definitely it is a boost converter, right? So this is actually a boost converter. This is actually a boost converter. Assume continuous conduction. So what is the another one? Assume continuous conduction. For boost converter, assume continuous conduction. We have to find out the peak blocking voltage of switch. Yes. What is the blocking voltage of switch in boost converter? Yes. Tell me, students. What is the blocking voltage of switch in boost converter? See, in the first mode, switch is in the on state, diode is off. In the second mode, diode is conducting, right? What happens when diode is conducting? Already capacitor is charged with V0 volts. So what is the voltage across the switch? V0. That means in boost converter, in the second mode when diode is in the on state, the switch is in the blocking state. Am I right? Already capacitor is charged with output voltage. So the entire output voltage across the capacitance appears across the switch. That means the switch has to block the maximum output voltage of the converter. So what is the blocking voltage of switch here? So in this case, the blocking voltage of switch in boost converter, the blocking voltage of switch is equal to maximum output voltage of the converter. Maximum output voltage of the converter. You know, alpha is not given here. So we have to find out the maximum blocking voltage of the switch. So what is the maximum blocking voltage of the switch? Maximum blocking voltage is same as maximum output voltage. That means we have to find out the maximum output voltage in this case. Right. Here it is not ideal case. They have given the resistance of this inductance. See, under ideal condition, we have one expression for average voltage. Here we have to consider the resistance of inductance. So after considering the resistance of inductance, what is the expression for average voltage here? So the expression for average voltage here, see, after considering the resistance, the expression for average voltage is Vs into 1 minus duty ratio divided by R by capital R plus 1 minus alpha whole square. Dear students, I hope you are already familiar with this equation. Capital R is the load resistance, small r is the resistance of inductor. Resistance of inductor is given, it is 0.1 ohm. See, resistance of inductor is 0.1 ohm and load resistance is 10 ohms. Supply voltage is 50 volts. Now, when will you get maximum output voltage? What is the condition for maximum output voltage in this case? How output voltage or transfer function varies with respect to duty ratio here? With respect to duty ratio, how the transfer function varies in this case? how the transfer function varies in this case. I think you are familiar. Under ideal conditions, what is the expression for average voltage? See, V naught is equal to Vs by 1 minus alpha. This is under ideal conditions. Under ideal conditions means resistance of inductance is 0. If you want to substitute, when resistance of inductance is 0 here, okay, you will get Vs by 1 minus alpha. Under this condition, when alpha is equal to 0, what is the transfer function? It is 1. So under ideal conditions, you see, under ideal conditions, when alpha is equal to 0, it is 1. When alpha is equal to 0.5, when alpha is equal to 0.5, 1 by 0.5, you will get 2. You will get 2 somewhere here. And when alpha is equal to 1 unity, it becomes infinite. So this is actually for ideal case. This is actually for ideal case. For ideal case, when resistance of inductance is 0. That means when that duty ratio approaches unity, the transfer function approaches infinite. But practically it is not possible. Practically, due to the resistance of inductance, you can see, practically due to the resistance of inductance, the maximum voltage will decrease after some time. So practically you can see here, it will decrease like this. So this is practical case. This is practical case. I hope you are familiar with this. So this is the maximum average voltage. We get maximum transfer function, and this is alpha maximum. So 0 to alpha maximum, the system is stable practically. That means we can operate the inverter up to this duty ratio. So what is the condition for maxima here? Condition for maxima, differentiate this equation with respect to alpha and then equate it to 0. So I want to find out the condition for maxima. So to find out the condition for maxima, differentiate this expression with respect to alpha and equate it to 0. So d by d of alpha Vs into 1 minus alpha by R by capital R plus 1 minus alpha whole square. So just differentiate this expression with respect to alpha and then equate it to 0. You will get the condition for maximum transfer function. Yes, can you calculate this value? After differentiating this one, what do you get? We get alpha maximum is equal to, I am not going to simplify this. If we simplify this, we get alpha maximum. So you will get alpha maximum is equal to 1 minus R by 1 minus square root of small r by capital R. So this is the maximum duty ratio. That means alpha maximum. Now substitute alpha maximum in this equation and calculate the maximum average voltage. You calculate the maximum average voltage here. So just look here. See, in this equation, you substitute alpha maximum. Alpha maximum is equal to 1 minus R by R under root. You can calculate this value. So you will get Vs into 1 minus Vs into 1 minus alpha. What is 1 minus alpha? See, directly I will write this value. See here, 1 minus alpha is equal to root R by R. Okay, root R by capital R by R by capital R plus, what is 1 minus alpha again? R by capital R. So I hope you understand 1 minus alpha whole square, na? I want 1 minus alpha whole square. Okay, so after simplifying this, finally what do you get here? After simplifying this, we get maximum average voltage. Okay, expression for maximum average voltage is Vs by 2 into again square root of small r by capital R. Okay, just simplify this. Okay. So finally, supply voltage is how much here? 50 volts. Supply voltage is 50 volts divided by 2 into, what is the resistance of inductance? It is 0.1 ohm. Resistance of inductance 0.1 ohm by load resistance is 10 ohm. Okay. So simplify this, you will get 250 volts. Am I right? You will get 250 volts. So what is the maximum possible output voltage in this converter? So in this converter, the maximum possible output voltage is 250 volts. The maximum possible output voltage is 250 volts. Now, what is the blocking voltage of switch here? The blocking voltage of switch is 250 volts. The blocking voltage of the switch is 250 volts. Okay, students? So answer is 250 volts. So that is the maximum blocking voltage of the switch. The peak blocking voltage of the switch is 250 volts. Okay, students? So is it clear now? So concept is clear? Did you understand this one? Yes, Dharmendra, you are right. Aditya also, you are right. Yes, Swati Gupta, right answer. Yes. So I hope the concept is clear to you. Okay. So it is a practical boost converter. The resistance of inductance is given in this case. We have to find out the blocking voltage of the switch. When diode is conducting in the second mode, the voltage across the switch is the load voltage. Maximum load voltage we have to find practically. So practically we get maximum load voltage at alpha maximum. So substituting alpha maximum in that equation, we can find out the expression for maximum average voltage. So this is the expression for maximum average voltage. You have to remember this. You will get 250 volts. So that is the maximum blocking voltage of switch. So answer is 250 volts. So I hope the concept is very clear to you, students. Okay? Right. Very good. So go through the next question, dear students. Next question, question number 6. Yes. So it is a very simple question. Yes, try to answer this question. Dear students, I will read out the question. The motor fed by load commutated inverter has to be operated at what power factor? So here the load commutated inverter, you can see the load commutated inverter. The load commutated inverter. What do you mean by the load commutated inverter? The load commutated inverter. See, load commutation is possible only when RLC satisfies underdamped condition. Underdamped condition. Underdamped condition. I think we have discussed in regular course. For underdamped condition, capacitive reactance is dominating inductive reactance. Dear students, in the regular course we have done the waveforms for this. Draw the current waveform, fundamental current waveform. When RLC satisfies underdamped case, RLC satisfies overdamped case. For underdamped case, capacitive reactance is dominating inductive reactance. When capacitive reactance is dominating inductive reactance, load commutation is possible. I hope the concept is clear. That means leading power factor. So it should be leading power factor. Why leading power factor? Because for underdamped condition, capacitive reactance is dominating the inductive reactance, then only commutation is possible. That means leading reactive power is needed for helping the commutation process. That means without a capacitor element, commutation is not possible. You can go through the commutation techniques. Without a capacitor, we don't have forced commutation. Right? Capacitor is a very important element for helping the commutation process. That means for helping the commutation process, we require leading reactive power. Leading reactive power is possible only when RLC satisfies underdamped condition, that is if capacitive reactance is dominating the inductive reactance. So answer is option C. So what is the question? The motor is fed by load commutated inverter so that it is operated at dash power factor. Unity power factor option A, option B lagging power factor, option C leading power factor, 0 power factor. So it should be leading power factor. Option C is the right answer. Okay students. So did you understand this question? Very simple question it is. Yes, good. Go through the next question. Question number 7. Yes, try to answer this question. Try to answer this question number 7. So I hope it is visible to you clearly, right? I'll read out the question now. Yes. Yes, Mr. Dharmendra, listen. Very good. Which of the following statements are true in a single phase fully controlled rectifier feeding RL load on DC side? Yes, try to answer this question. Which of the following statements are true in a single phase fully controlled rectifier? So what is this one? Single phase fully controlled rectifier. Single phase fully controlled rectifier feeding RL load. Feeding RL load. So it is a single phase fully controlled rectifier feeding RL load on DC side. Which statements are true here? So 4 statements are given here. I will read the statements. Option A. Option A, what is the statement here? So what is the statement in option A? Average output voltage depends only on firing angle. Yes. Option A, the statement is average output voltage depends only on firing angle. Statement B. Statement B, average output voltage depends on firing angle. See, in statement A, average output voltage depends only on the firing angle it is given. In statement B, average output voltage depends on firing angle. That means it may depend on some other parameters also sometimes. Statement C, average output voltage depends on load impedance. See the statement C. Average voltage depends on load impedance. Is it true or wrong? See, naturally in phase controlled rectifiers, average voltage depends on alpha. See, average voltage depends on alpha. That is right. Average voltage depends on firing angle alpha. Okay. So average voltage depends on alpha. Now my question is, check whether average voltage depends on load impedance or not here. Yes. Can you answer this question? Average voltage depends on load impedance or not? Yes. Anurag, Dharmendra, Aditya. What is your answer? Average voltage depends on load impedance or not? Load is RL load. See, this is very familiar. Average voltage definitely depends on firing angle alpha. No doubt, that is right answer. What about other statement? Average voltage depends on load impedance or not? Average voltage depends on load impedance or not? Average voltage also depends on load impedance. This is also right answer. Why it depends on load impedance? See, in the case of RL load, you may get continuous conduction or you may get discontinuous conduction. For RL load, when it is discontinuous conduction, average voltage depends on beta and beta depends on time constant of the load. Do you remember? See, for discontinuous conduction, you see here, RL load discontinuous conduction. RL load discontinuous conduction. RL load discontinuous conduction. Do you remember what is the output current waveform here? What discontinuous conduction? Current will start here. This is alpha to beta. Alpha to beta. You know, in full bridge rectifier, T1 and T2 will conduct from alpha to beta. So here beta depends on load impedance. Beta depends on load impedance. Load impedance or time constant of the load is L by R ratio. I think in the regular course we have studied extinction angle beta depends on the time constant of the load, L by R ratio, otherwise load impedance. So for discontinuous conduction, what is the expression for average voltage? Do you remember discontinuous conduction? What is the waveform for V naught? Alpha to beta when T1 T2 is conducting, alpha to beta when T1 T2 is conducting, when T1 T2 is conducting, V naught is equal to Vs. Okay, after that T3 T4 will conduct. One more waveform repeats. I am not drawing all the waveforms. So what is the expression for average voltage here? Vm by time period of the pulse is pi cos alpha minus cos beta. So see here, average voltage depends on beta, beta depends on load impedance. Average voltage depends on beta here and beta value depends on load impedance. That means when it is discontinuous conduction, average voltage also depends on load impedance. Understood? So that means this statement is also right. So statement B is right. Okay, statement B is right. Statement C is right. Last statement. Go through the last statement. First statement is wrong. Average output voltage depends only on firing angle. No. Average voltage depends on firing angle and also on load impedance. When it is RL load. When it is RL load. Remember, when it is RL load. Okay. Statement D. The current ripple factor is lesser than voltage ripple factor on DC side. You see, because of inductance, if inductance increases, what happens? Inductance increases, smoothness of the current waveform improves. Smoothness of the current waveform improves. Okay. If the smoothness of the current waveform improves, what happens? Form factor decreases and therefore current ripple factor decreases. That means for inductive loads, the shape of the current waveform depends on load inductance. Am I right? For inductive loads, the shape of the current waveform depends on load inductance. Otherwise, the smoothness of the current waveform depends on load inductance. So as the load inductance increases, the current ripple factor is minimized. That is why current ripple factor is lesser than voltage ripple factor on DC side. So statement D is also right answer. So what is the statement D? The current ripple factor is lesser than voltage ripple factor on DC side. Why the current ripple factor is reduced in this case? The current ripple factor is reduced due to the inductance. Due to the inductance, smoothness of the current waveform improves, right? So that is why current ripple factor is reduced in this case when you compare with voltage ripple factor. So that is why statement D is also right answer. So it is MSQ questions. So this MSQ. So this question is MSQ based. That means in GATE, last year in GATE 2021, they have introduced multiple select questions. In multiple select questions, you may have one right answer or you may have more than one right answers. So here we are having three correct options. So what are the three correct options? B, statement B, statement C and statement D. So three statements are right. So option B, C, D. So these are the right answers. Okay students. So concept is clear to you. This is concept oriented questions. Okay. Concept oriented questions. Yes. So response is very good. So Dharmendra, are you okay? Yes, very good. Thank you for your response. So concept is clear now. This is concept based MSQ questions, concept based MSQ questions. So students should understand the concept very clearly. Okay, good. Go through the next question. Question number 8. Yes, see this question. Yes, try to answer this question. I will give you 2 minutes time. Yes, try to answer this question. Make it fast. Yes, students, try to answer this question. Yes, make it fast. First, identify what is the converter here. Dear students, identify what is the converter. Is it buck converter or boost converter or buck boost converter? Identify the converter. Inductor is placed near the supply side. So definitely this is actually a boost converter, right? It is actually a boost converter. Okay, it is actually a boost converter. We have to find out the peak value of current passing through the switch. See, what current is passing through the switch? When the switch is in the on state, the peak value of current passing through the switch is same as peak value of inductor current. See here, the peak value of current passing through the switch. If I write SW, that is switch. The peak value of current passing through the switch is same as the peak value of inductor current. Is same as the peak value of inductor current. Am I right? See the circuit diagram. When you turn on the switch, in the first mode L is storing energy. So the current is passing through the switch. So the peak value of current passing through the switch is same as the peak value of inductor current. What is the peak value of inductor current? I maxima. So we have to find out the maximum current passing through the inductor. I have given the hint, students. Dear students, I have already given the hint for you. The peak value of current passing through the switch is same as the peak value of inductor current. The peak value of inductor current means I maxima. Yes, try to answer this question. Make it fast. Make it fast. Try to answer this question. Yes, Saujanya, Vivek, Dharmendra. Yes, try to answer them. So Aditya has given one answer. Yes, try to answer this one. So one of the student has given right answer. Yes, very good. Just you should be very careful here. So normally student will do one mistake here. So be careful. Go through the given data. Okay. Mr. Satyam, very good. Your answer is correct. Yes. Sanjay Kumar Verma. Yes, right answer. Shivam, check it. Exactly. Bunny has identified. Very good. Dharmendra, you are right. Yes. Okay, students. Here, if you observe the given data, inductive current is in discontinuous mode. How can you identify that inductive current is in discontinuous mode? Say for boost converter, average voltage is equal to Vs by 1 minus alpha. Right. Supply voltage is 20 volts by 1 minus duty ratio 0.6. Duty ratio is 0.6. So calculate this value. If you calculate this value, you will get 20 by 0.4, 50 volts. 50 volts. But what is the given average voltage here? The given average voltage is 60 volts. So here given average voltage is 60 volts. This value is greater than Vs by 1 minus alpha. See, Vs by 1 minus alpha is 50 volts. Okay, but given average voltage is 60. So given average voltage is more than Vs by 1 minus alpha. That means inductive current is discontinuous here. So here, therefore inductive current is discontinuous. Inductive current is discontinuous. Okay. So if inductive current is discontinuous, what is the shape of inductive current here? When the switch is turned on, it starts from 0. Okay. Then after that, switch is turned off. Up to here, switch is in the on state. Then after that, diode is in the on state. So if you observe here, so this is actually the ripple, delta L, I maxima. So here, when it is discontinuous conduction, I maxima is same as ripple. I minima is 0 here. For discontinuous conduction, I minima is equal to 0. And I maxima is equal to delta L. For discontinuous conduction, I maxima is equal to delta L. What is the expression for ripple in boost converter? See, the expression for ripple in boost converter is alpha Vs by Fl. This is the expression for ripple in the boost converter, alpha into Vs by Fl. So calculate this value, alpha into Vs. So given alpha is 0.6, Vs is 20. So 0.6 into 20 divided by frequency 15 kilohertz. So 15 into 10 power 3, this is the frequency, multiplied by the inductance is 100 microhenry. So 100 into 10 power minus 6. 100 into 10 power minus 6. So if you calculate, this value is 8 amperes. 8 amperes. So that is the ripple current. So if you observe here, the peak value of current passing through the switch, the peak value of current passing through the switch is I maxima, that is delta L, that is 8 amperes. So answer is 8 amperes. So I hope students, everyone understood this concept. So here, student should identify that it is discontinuous conduction. Okay, so it is discontinuous conduction here. Okay, when it is discontinuous conduction, the peak value of current passing through the inductor is same as ripple current. The peak value of current I maxima is same as ripple current in the inductor. Ripple current in the inductor for boost converter is alpha is the duty ratio into Vs by Fl. This is the expression for ripple current. Okay, so substitute the parameters, answer is 8 amperes. Okay students, so I hope it is clear to you. Yes, very good. Okay. Okay students, go through the next question. See the next question here. Question number 9. Yes, try to answer this question. I'll read this question. Just note down. A 3-phase voltage source inverter delivers power to a star connected resistive load of 10 ohms per phase from a 450 volts DC supply. It is operated in 180 degree mode. The RMS value of Thyristor current is, that means here it is a 3-phase VSI operated in 180 degree mode. Okay, 3-phase VSI. So 3-phase VSI 180 degree mode. 180 degree mode, star connected load. Star connected load. Of course, it is resistive load, right? So, do you remember the waveform for R phase voltage? See, this is star connected resistive load here. Star connected resistive load here. Okay. Star connected resistive load. Small r is the load resistance. So here load resistance is 10 ohms per phase. Load resistance is 10 ohms. So the DC supply voltage is 450 volts. It is given very clearly. We have to find out the RMS value of Thyristor current. So what is the phase currents here? See here, this is Y phase, R phase and B phase. So what is the R phase current? So I hope you are familiar with R phase current here and R phase voltage. See, let me draw the waveform for R phase voltage. Dear students, 3-phase VSI, whether it is 180 degree mode or 120 degree mode, students should remember the waveforms for the line voltage VRY. You must remember these waveforms. The line voltage VRY. Line voltage is same for star and delta loads. See, whether it is star connected load or whether it is delta connected load, the line voltage VRY remains same. For a star connected load, R phase voltage you have to remember. So these two waveforms student should remember for examination point of view. If student remembers these two waveforms for 180 degree mode and 120 degree mode, then definitely you can answer any question in 3-phase VSI. To answer any question in 3-phase VSI, student must remember these waveforms. You have to remember R phase is a 6-step waveform. You have to remember this waveform for examination point of view. It is actually a 6-step waveform. So I hope you remember this. So this is Vs by 3 and this is 2Vs by 3. So this is pi by 3, this is 2 pi by 3 and this is pi and symmetrical negative pulse. So what is the R phase current here symmetrically? For resistive load, feedback diodes will not conduct, only thyristors will conduct or only switches will conduct. So for resistive load, R phase current is similar to R phase voltage. So even R phase current is a 6-step waveform. Even R phase current is a 6-step waveform like this. So R phase voltage for the first 60 degrees, R phase voltage is Vs by 3. See, R phase voltage is Vs by 3. So what is R phase current divided by R? So this is Vs by 3 into R. This is 2 into Vs by 3 into R and so on. Now R phase voltage positive, R phase current positive, power positive. Here instantaneous power is always positive. So only switches will conduct. Switches means thyristors. Feedback diodes will not conduct because the load is pure resistive load. So let us suppose that what is the positive group thyristor of R phase? S1 or T1 if it is thyristor. Next, negative cycle, R phase voltage negative, R phase current negative, power positive. So what is the switch which belongs to the negative group? This is T4 or S4. T4 or S4. Okay. So T1 gives positive R phase current and T4 gives negative R phase current. So we have to find out the RMS value of current passing through thyristor. See, RMS value of current passing through thyristor. See, for this very simple, here what is the line voltage VRY here? Line voltage RMS. What is the line voltage RMS? It is root 2 by 3 into supply voltage, DC supply. Dear students, you have to remember this formula for examination point of view. This is the expression for line voltage RMS in the case of 180 degree mode VSI. For star connected load, what is R phase voltage? R phase voltage RMS is line voltage by square root of 3. Okay, so you will be getting root 2 into Vs by 3 volts. Okay, if you want you can cross check here. For this waveform, you find out the RMS value, you will get root 2 into Vs by 3. So what we have to calculate here in this question? We have to find out the RMS value of Thyristor current. So what is the RMS value of phase current here? RMS value of phase current is phase voltage by load resistance. Phase voltage is root 2 into Vs by 3 into R. Okay. Now I want to find out RMS value of current passing through each thyristor. See, RMS value of current passing through each thyristor. Each thyristor is conducting the phase current. See, here T1 is conducting the phase current. Look here, this is nothing but phase current, no? This is nothing but phase current. Okay, T1 is conducting the phase current. T1 is conducting the phase current for pi radians out of 2 pi radians. T1 is conducting the phase current for pi radians out of 2 pi radians whole power 1 by 2. Can I write the expression like this? Say T1 is conducting the phase current for pi out of 2 pi whole power 1 by 2. So that is equal to phase current RMS divided by square root of 2. I think we have calculated phase current RMS. Phase current RMS is root 2 Vs by 3R. So phase current by root 2 means it becomes Vs by 3R amperes. Vs by 3R amperes. So this is the expression for RMS value of current passing through each thyristor for star connected resistive load in the case of 180 degree mode VSI. This is the expression. Now supply voltage is how much? 450 volts. Supply voltage is 450 and load resistance is 10 ohms. So this comes to be how much? 15. So that is equal to 15 amperes. So therefore RMS value of current passing through each thyristor is 15 amperes. Okay students. So answer to this question is 15 amperes. Option B is the right answer. 15 amperes is the right answer. So here, to answer all the questions in 3-phase VSI, examination point of view, student should remember the waveforms for the line voltage VRY, which is common for star and delta connected loads, and we have to remember the waveform for R phase voltage. If you remember these two waveforms, definitely student can answer any question in 3-phase VSI. That means when you write down the short notes, what you have to remember for examination point of view, that is important. You cannot memorize each and every formula examination point of view. So in each case, what we have to remember for examination point of view, so that we can answer any question, that is the way you have to prepare, right? So right students, go through the next question number 10. Go through the question number 10 now. Question number 10. Dear students, 10th question. In a single phase full bridge inverter, supply voltage varies in a range of 295 to 325 volts. So look here, this is a single phase full bridge inverter. Single phase full bridge inverter, the supply voltage, that is the DC supply voltage, it varies from 295 to 325 volts. That means the DC supply voltage is fluctuating between 295 to 325 volts. Next, the output voltage is required to be constant at 200 volts RMS value. That means the output voltage is, that means the RMS value of output voltage is, so here the output RMS voltage, it is 200 volts. This is actually RMS value. Then maximum RMS current, the maximum RMS current is 10 amperes. It is 10 amperes. Here output current is sinusoidal, that is assumption, sinusoidal. See here, in the assumption they have given, assume the load current is sinusoidal waveform. Assume the load current is sinusoidal waveform and the maximum RMS current is 10 amperes here. Calculate the combined switch utilization ratio. So what is the meaning of switch utilization ratio? So first let me explain about switch utilization ratio. Switch utilization, switch utilization ratio. switch utilization ratio, SUR. SUR means switch utilization. That means how effectively we are utilizing the switches in the converter. So switch utilization ratio means it is a measure of utilization of switches with respect to ratings. Okay, I will give the mathematical expression to calculate the switch utilization ratio. Maximum output voltage volt amperes. So it is maximum output volt amperes. Maximum output volt amperes divided by Q into VT into IT. Here, what is the maximum output volt amperes? Maximum output voltage into maximum RMS current. This is the maximum output volt amperes divided by Q into VT into IT. So here Q means number of switches. So here Q means number of switches. Yes, dear students, can you tell me, this is a full bridge inverter. In the case of full bridge inverter, totally how many switches? Each leg we are using 2 switches. So 2 legs we have in full bridge inverter. So number of switches in full bridge inverter is 4. So we are having 4 switches in full bridge inverter, right? Next, what is VT? VT means the peak blocking voltage of switch. VT means it is the peak blocking voltage. The peak blocking voltage of switch. The peak blocking voltage of switch. The peak blocking voltage of switch. See, in the case of full bridge inverter, can you tell me what is the blocking voltage of switch? Yes, try to answer this. And IT means it is the peak current passing through the switch. It is the peak current. It is the peak current in switch. Peak current in switch. So we have to find out the peak blocking voltage of switch. VT is the peak blocking voltage of switch. IT is the peak current in the switch. Yes. Just go through the circuit diagram for full bridge inverter. See. Go through the circuit diagram for full bridge inverter. You will understand this one. In VSI, across each switch we have anti-parallel diode or feedback diodes. This is leg A. And we are having another leg B. Okay, we are having another leg B. I think you are familiar with this circuit diagram. Okay, this is the DC terminals where we are giving DC supply. Okay, across the AC terminals leg A and leg B. Across the AC terminals we are connecting the load. This is the AC load. Load voltage and load current is I0. Okay. Now, what is the blocking voltage of switch here? Suppose if this device is in the on state, what is the voltage across the switch? Vs. That means what is the maximum blocking voltage of each switch? The maximum blocking voltage of each switch is same as the supply voltage. That means whether it is half bridge inverter or whether it is full bridge inverter or whether it is 3-phase VSI, in all the 3 cases, when the upper device is in the on state, the entire DC supply appears across the bottom device. Okay. That means what is the blocking voltage of each switch? Blocking voltage of each switch is maximum voltage of DC supply. What is the maximum voltage of DC supply? 325 volts. Because we have to design the ratings or specifications for the worst case. See, I want to design the voltage rating of switch. The voltage rating of switch is what? Maximum voltage of DC supply. What is the maximum voltage of DC supply? It is 325 volts. So here VT is equal to maximum DC voltage. Maximum DC voltage of supply, that is 325 volts. Okay. Next, what is the peak current passing through the switch? Here the load current is assumed to be sinusoidal. The load current, this is the load current. Assume the load current is sinusoidal. So what is the RMS value of load current here given? Here, what is the RMS value of load current here? RMS value of load current? It is 10 amperes. So here the load current is assumed to be sinusoidal, RMS value of 10 amperes. So the peak value is 10 root 2. No? See, the load current is assumed to be sinusoidal. RMS value of load current is 10 amperes means what is the peak value of load current? 10 into root 2. So peak value of load current is 10 into root 2. What is the maximum current passing through the switch? Maximum current passing through the switch is root 2 times maximum RMS load current. So root 2 times 10 amperes. So that is the peak value of current passing through the switch, 10 root 2. So 10 root 2 is the peak current passing through the switch. Okay students. So now substitute in this case and find out the switch utilization ratio. Yes, let us find out the switch utilization ratio. Okay. So that is equal to RMS output voltage. What is the RMS output voltage of output here? See, what is the RMS value of output voltage here? Yes, 200 volts. See, the output voltage is 200 volts RMS voltage. So RMS voltage is 200 volts into maximum RMS current is 10 amperes. 4 switches we are having. Blocking voltage of each switch is 325 volts into the maximum current passing through the switch is 10 into root 2. So just calculate this value. Tell me what is the answer here. Yes, make it fast. Calculate this value. So 200 into 10 by 4 into 325 into 10 root 2. If you calculate, you will get 0.11. So this is the switch utilization ratio. So answer is 0.11. Okay, 0.11. So option C is the right answer. So just go through this, all of you. So students should understand what is the meaning of this switch utilization ratio. Okay students, just go through this question now, all of you. So everything is very clear to you. So if you have any doubts. Okay students. Yes, what happened to you? So option C is the right answer. Okay. Okay, go through the next question students. Question number 11. Yes, question number 11. Which of the following statements are true with PWM inverters? Yes. Question number 11. Which of the following statements are true with PWM inverters? With PWM inverters. See, first statement. Asynchronous PWM results in subharmonics. See, what is synchronous PWM? What is the meaning of synchronous PWM? In the case of synchronous PWM case, MF is integer. This MF is integer here. Asynchronous PWM. Asynchronous PWM. In the case of asynchronous PWM mode, MF is non-integer. MF is non-integer. See, if MF is non-integer, then it will introduce subharmonics in the output voltage waveform. So asynchronous PWM introduces subharmonics. That is the problem. Subharmonics in the output voltage. That is why most of the practical applications we try to avoid asynchronous PWM. Mostly we prefer synchronous PWM. Do you remember when I was explaining in regular course about unipolar PWM, bipolar PWM? Every time I used to say MF is integer. Sometimes it is odd integer, sometimes it is even integer. Ultimately it is integer only. Because always we try to get synchronous PWM. Right? In the case of asynchronous PWM, it is non-integer. What is the drawback of asynchronous PWM? In the case of asynchronous PWM, it will introduce subharmonics in the output voltage waveform. In the case of asynchronous PWM, it will introduce subharmonics in the output voltage waveform. So that is why it is not preferred for most of the applications. Okay. So first statement, asynchronous PWM results in subharmonics that are undesirable in most of the applications. Yes, first statement is true. Second statement, the modulation ratio MA less than or equal to 1. Modulation ratio is less than or equal to 1 means it is linear modulation. This is linear modulation. In the case of linear modulation, the PWM pushes the harmonics into the high frequency range. That means here second statement MA less than or equal to 1, linear modulation. In that case, the PWM inverter pushes the harmonics into high frequency range. That means the harmonics are shifted into the high frequency range nearby switching frequency or carrier frequency. Yes, that is true statement. So statement B is also right answer. What is statement B? Linear modulation. The PWM inverter pushes the harmonics into high frequency range. Yes, that is true. Third statement, blanking time on output voltage in PWM inverter introduces lower order harmonic. First of all, what is blanking time? See here, I will explain what is the meaning of blanking time here. See, here we are having inverter here, leg A. This is leg A. This is the inverter leg A. See, in this inverter, these two switches are complementary. Am I right? These two switches are complementary. This is the DC voltage. Here, these two switches are complementary, S1 and S4. Let it be. If I switch on S4 before S1 stops, that will short circuit the DC source. See here, if I switch on S4 before S1 stops, that will short circuit the DC source. To avoid the short circuit, we have to leave some space for commutation to allow the turn off process, because switches are not ideal. Every device is practically taking some turn on time, practically taking some turn off time. So we have to leave some space to allow the turn off process of the respective switches. That means we have to leave some time for allowing commutation process here. That is called blanking time. Okay, so what is blanking time here? Before you switch on S4, we have to leave some space. That means from here to here S1 is conducting. After that, leave some time delta Q. That is the turn off time for, leave the turn off time for S1. Delta Q is the turn off time of S1. Then we will switch on S4. So because of this blanking time, that is going to introduce lower order harmonics. That is one of the disadvantage here. So blanking time introduces lower order harmonics. Blanking time introduces lower order harmonics in PWM. Okay. So statement C is right. Blanking time on output voltage introduces lower order harmonics. C is right. Statement D, blanking time on output voltage in PWM inverter eliminates the lower order harmonics. No, that is wrong. Last statement is wrong. So blanking time is introducing lower order harmonics. That is one of the drawback of blanking time. Okay. So A, B, C, three statements are correct here. So statement A, B and C, three statements are correct here. Okay students, so just go through the question once again. Go through this question once again. Which of the following statements are true with PWM inverters? First statement, asynchronous PWM results in subharmonics, and that is undesirable for most of the practical applications. So first statement is right answer. Second statement, for linear modulation MA less than or equal to 1, the PWM pushes the harmonics into high frequency range. Yes, that is also true. Third one, blanking time will result in lower order harmonics. That is also drawback. That is also true. So A, B, C statements are right here. Okay. Next question number 12. Yes. Go through the question number 12 here. In the single phase bridge inverter, see question number 12. In the single phase bridge inverter, the load current is I0 is equal to 540 into sine omega t minus 45 degree. The DC supply voltage is 300 volts. What is the power delivered to the load here? So you see here, what is the power delivered to? So this is a single phase full bridge inverter. Single phase full bridge inverter. Single phase full bridge inverter. So supply voltage is DC. Supply voltage is DC. It is 300 volts. 300 volts. And output is load here. This is also AC. So output is load and output current is sinusoidal here. The shape of output voltage is square wave here. See, the shape of output voltage is square wave. I think it is very clear to you. The shape of output voltage is square wave. This is the shape of output voltage. And then what is the shape of output current here? The shape of output current is sinusoidal. See, what is the equation of I naught? Equation of I naught is 540 into sine of omega t minus 45 degree. Okay, that means the output current is lagging by 45 degree. Output current is lagging by 45 degree. The peak value is 540 amperes. Okay, okay students. So how to find out the output power? Output power is same as fundamental power. Output power is same as fundamental power. Reason is we are having output current is pure sinusoidal. Output current is pure sinusoidal at fundamental frequency. That means we are having output current component at fundamental frequency. So output power and fundamental power are same. So what is fundamental power? Fundamental RMS voltage into output RMS current into cos of phase angle difference. So what is fundamental RMS for square wave? See, nth harmonic RMS for square wave is 4 Vs by n pi divided by square root of 2. So that is 2 root 2 by n pi into Vs. This is the nth harmonic RMS value. So what is fundamental RMS value? Fundamental RMS is 2 root 2 by pi into Vs. Okay, this is fundamental RMS value. So let us find out the output power. Output power is same as fundamental power. So fundamental RMS voltage is 2 into root 2 by pi into DC supply is 300 volts. So this is the fundamental RMS. See, this is 300 volts. This is 300 volts DC supply. I substituted. Then what is the RMS value of output current here? See, the peak value of output current is 540 amperes. So RMS value is, so what is the RMS value? The peak value is 540. Its RMS value is 540 by square root of 2. That is the RMS value of output current. Multiplied by, what is the phase angle difference? 45 degrees. So cos 45 degrees. Cos of 45 degrees. Okay. So simplify this value and calculate the output power, which is same as fundamental power. So after calculating this, how much you get? So just calculate this. You will get 72.93 kilowatts. 72.93 kilowatts. Okay students. So just observe this one. So it is very clearly given. Output voltage is square wave. Output current is pure sinusoidal, lagging by 45 degrees. Whenever the output current is sinusoidal at fundamental frequency, output power is same as fundamental power. That is the point you have to understand. Okay. Then the last question. Go through the last question. Dear students, go through the last question. So this is a midpoint rectifier. Find out the PIV of the thyristor. Right students? Try to find out the PIV of the thyristor. This is the last question for this session. Okay students? Try to find out the PIV. PIV of the thyristor. It's a midpoint rectifier. Yes, make it fast. Try to find out the PIV. What happened to you all? Try to find out the PIV. Yes. What is the PIV? See, if you observe here in midpoint rectifier, the turns ratio is not same here. Just observe this one. The turns ratio is not same here. 1:2. See, 1:2:1. That means upper secondary 2, bottom secondary 1. Here in the positive cycle, this is plus minus, plus minus, plus minus. In the positive cycle, when T1 is conducting, what voltage appears across T2? T2 is reverse biased, no? So voltage across T2 is the entire secondary voltage appears here. So that is 3 times the supply voltage. So here PIV of the thyristor is PIV of each thyristor. PIV of each thyristor is equal to the peak voltage of secondary, the peak secondary voltage. The peak secondary voltage. Why I have to consider the peak secondary voltage? Here when T1 is conducting, the entire secondary voltage of transformer appears negative voltage across T2. See, when T1 is conducting in the positive cycle, the entire secondary voltage appears reverse voltage across T2. What is the maximum secondary voltage? It is actually 3 times the primary voltage. So peak secondary voltage is 3 times. So 3 times the peak voltage of supply is 230 root 2. 230 into square root of 2. Okay. But if you observe here, the supply voltage is fluctuating 10 plus or minus 10%. See, the supply voltage is fluctuating. It is not constant. So that is why when the supply voltage is fluctuating, you have to consider the PIV for the worst case. So peak secondary voltage, okay, peak secondary voltage plus additionally 10% of peak secondary voltage you have to write, plus additionally 10% of peak secondary voltage. Okay, so plus 10% means 10% of 3 into 230 root 2. Okay, so calculate this value and tell me what is the answer here. See, voltage across thyristor T2 is entire secondary voltage, 2 turns, 1 turn, totally 3 times. Secondary turns ratio is, you can simply write it is 1:3. So secondary turns ratio is 3 times, 2 plus 1, 3 times. So maximum secondary voltage is 3 times the peak voltage of AC supply, plus additionally voltage is fluctuating, so 10% of this voltage. So just calculate this value. You will get, this is 975.8, this is 975.8 plus 10% of 975.8. Why we are adding 10% here? Because voltage is fluctuating. So if it comes to be 1073.38 volts. So that is the PIV of each thyristor in this case. So here we should be very clear. In regular course we will write 1:1:1, but I have taken 1:2:1. Normally PIV of the thyristor in midpoint rectifier, unfortunately the mistake is 2 Vm you will write, but here turns ratio is changed here. That means the PIV of the thyristor in midpoint rectifier is the peak secondary voltage of transformer. Simple way, the peak secondary voltage of transformer is, turns ratio is 3 times, so 3 times the peak voltage of supply. Because of voltage is fluctuating, so 10% of that voltage we have to add. So that is why the answer comes to be, the PIV of each thyristor is 1073.38 volts. Okay students, so I hope concept is very clear with this question. So many students have answered. Very good. Right students? Okay, good. Right students? So only 1 hour was allotted for GTQ course in power electronics. I have taken almost 1 hour, 1.5 hours I have taken. 2 hours, I think. Yes, 2 hours. 6 o'clock I started now. So I have taken 2 hours to complete this course. We have done totally 13 questions. Right, students? Power electronics, don't worry about power electronics. No need to memorize all the formulas. Remember that. 80% of formula no need to memorize in power electronics. Understand the concept. Okay. You can answer most of the questions in power electronics. Only 10 to 15% of formulas should be memorized in a proper sequential order. That comes by practice. So dear students, by this time you might have practiced the workbook questions in regular course at least 3 times, and you might have done revision through GATE, and we have Made Easy has given lot of support to the students community. So we have given, along with the regular course, Made Easy has given you some additional courses for revision. What are the additional courses Made Easy has given? Revision through GATE questions we have given, and we have given summary of all chapters, all the subjects, quick revision program. So quick revision program, we have given the summary for each and every chapter for all the subjects, so that it will be very much helpful for the students to summarize the concepts, so that less time they can summarize many things. So that course will be very helpful to you. So no need to learn new things in power electronics. Whatever you listen my regular course and whatever you practice, it is sufficient. I have solved the little bit worst questions in this case, tough questions only. Remaining students, you can practice the questions in PWM inverters based on amplitude modulation ratio, frequency modulation ratio, and remaining numericals we have already done in our regular course. Practice them. Okay students, all the best for your bright future. Thank you so much. Thank you students. Thank you students. I am leaving the class. Okay. Okay.